So this is our lecture on Chapter 17, Free Energy and Thermodynamics. So we're going to start by remembering the first law of thermodynamics, which is that the total energy of the universe does not change. It is only transferred from one place to the other. So the total energy of the universe is going to be equal to the system plus the surroundings. And the total change of energy in the universe is always going to be equal to 0. For an exothermic reaction, remember exo like exit, the system loses heat into the surroundings. There's two ways this heat is lost. It's either converted to heat Q or used to do work W. So we look at the delta E equation. Delta E can be thought of as Q plus W, heat plus work, or you can substitute enthalpy in there for Q and get delta E equals delta H plus P delta V. Remember, delta E is a state function, meaning it doesn't mean the path you take. That doesn't matter. It only matters where you start and where you end. Energy tax is the idea that in order to recharge a battery, some of the energy is actually going to be lost. So to recharge a battery with 100 kilojoules of useful energy, you need to use more than 100 kilojoules. This is something like if you get rechargeable batteries for your cell phone or any battery that's recharged, it actually takes more than the set amount of power to get that charge because of the energy tax, because inherently there's going to be some energy lost in the transfer. Every energy transition results in some kind of loss of energy. The conversion of energy heat, which is lost by heating up the surroundings, it's almost impossible to keep all that energy in. So for example, if you're heating your iPhone, if you actually touch the base of the charger, what you plug into the wall, it's actually going to be hot. And what you're losing there is some of the energy to the surroundings. It's becoming hot from that exchange of electrical energy. Thermodynamics, remember, predicts whether a process will proceed under a given condition. Thermodynamics is the study of the energy change in a reaction. We're going to say reactions are either spontaneous or non-spontaneous. Spontaneous is when a reaction will occur without an input of energy. A non-spontaneous process requires energy to move forward. So an example of a non-spontaneous process, which most reactions are, would be the flame test lab we've done, lighting a match, burning fossil fuel. These are all things where you have to start the reaction with energy and then the reaction will proceed. Most spontaneous processes are some kind of decomposition reaction where the substance will decompose and you won't need any energy going in to start that process. Spontaneity is determined by comparing the free energy of the system before the reaction with the free energy of the system after a reaction. Free energy is basically just what it sounds like. It's the amount of energy available to do work in a system, or the amount of energy free to do something else. If the system after the reaction has less energy than before the reaction, we say the reaction is thermodynamically favorable or spontaneous. So in order for a reaction to be spontaneous, the system after has to have less energy than the system before. Basically, the reactants have to have more energy than the products. Spontaneity has nothing to do with how quick or slow the reaction goes. Basically, it just means will the reaction occur on its own, or will you need to do some input of energy to get the reaction to start? The direction of spontaneity can be determined by comparing the potential energy of the system at the start and at the end. The direction means whether it's going to be spontaneous in the forward process, meaning a regular reaction, or in the reverse process. Any spontaneous process is irreversible. It can only proceed in one direction, meaning you can't go back. Some processes we're going to see can reach a state of equilibrium where things are breaking down and new bonds are forming kind of concurrently. But if you have a spontaneous reaction, you cannot go backwards. A reversible process will proceed back and forth, and we will get in the state of equilibrium. This means there's going to be no change in free energy. Things are just moving back and forth. Now remember, equilibrium is pretty much the same no matter how you're defining it. So most people know equilibrium in terms of osmosis with the water flow in cells, and it's really the same process. But when we talk about reversible processes in equilibrium or thermodynamic equilibrium, we're talking about there's no net change in free energy. If a process is spontaneous in one direction, it is automatically going to be non-spontaneous in the opposite direction. There's two main factors that determine thermodynamic favorability, so whether or not it's going to be spontaneous or non-spontaneous. We've talked about one of them. Delta H is enthalpy. This is basically a measure of the bond energy, or the amount of energy needed to break a bond. Remember, enthalpy is an inherent property of most compounds, where we're going to talk about how much heat can come out of the breaking or making of bonds in that specific compound. Entropy is something new. Its symbol is S. Yes, they sound very much the same. You have enthalpy and entropy, but they are two very different things. Entropy is the randomness or orderliness of a system. Remember that in nature, most things tend towards orderliness. Things want to be stable, things want to be orderly. So entropy is a measure of how orderly or random or chaotic a system is at the start and how that changes. This factor is generally more important than entropy when we talk about spontaneity. Enthalpy is related to the internal energy. It's usually measured in kilojoules per mole. It's a measure of how much energy is contained in the bonds. The stronger the stronger bond there is, the more stable the molecules, which is going to mean the more energy is needed to break up those molecules. If the products are more stable than the reactants, energy is released, and you're going to get a negative H in an exothermic reaction. If the reactants are more stable, energy absorbed, you're going to get an endothermic delta H positive reaction. The enthalpy is favorable for exothermic reactions and unfavorable for endothermic reactions. So if we look at Hess's law, which we've done problems in the previous chapter, the delta H degree, remember degree sign always means standard, which means you're going to look it up. It's going to be in a chart somewhere, it's going to be given somewhere, is equal to the sum of the delta H change of the products minus the sum of the delta H changes of the reactants. And you can see in this graphic, this is showing you the state function. So you can see where you start up here and where you end, and in terms of the state function, we just care about what this total change was. Entropy, again, is the orderliness, how orderly the particles are. Entropy is a thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increase. Basically, it's kind of a measure of how orderly the particles are arranged. Are they in a very strict set arrangement, or is there some fluidity to their arrangement? This is generally measured in joules per mole, and this is where you get a slight problem, because if you're going to do a problem with delta H and delta S, you have to have them in the same unit. And usually delta H is measured in kilojoules, entropy is measured in joules, but we know how to change that pretty easily. The random systems require less energy than ordered systems. You don't need as much energy to break bonds of random systems because it's already so chaotic anyway. This equation for calculating entropy that you're going to see there, you're not going to use a whole lot. You're mostly going to use standard entropies and use them to calculate overall entropies, but the way you calculate total entropy is we use something called a Boltzmann constant, which is just like all the other constants we've talked about, H and C and all the other ones. That is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. And then we're going to take the ln, the natural log of W, which is the number of energetically equivalent ways, or the number of ways you can arrange the particles. Again, entropy change is favorable when the result is a more random system, or when delta S is positive. Some changes that increase the entropy, and these are important because you will see these in multiple choice and free response question. Reactions whose products are in more disordered state. So in general, solid state is the most orderly, liquid's the middle, and gas is the least orderly. So when you're comparing something in its gaseous state versus stable state, the stable state is always more orderly, less random. Gases are always more random. Reactions which have larger numbers of product molecules than reactant molecules. So when you count, the less molecules there are, the more stable they are. With temperature, remember that temperature is a measure of the kinetic energy of particles. So the faster particles are moving, the more disordered they are. And solids dissociating into ions. A solid compound is more stable than the ions when it breaks up into water. So if we're going to get the total change in S of a system, you're going to take the final entropy minus the initial entropy. We're going to bring in now the second law of thermodynamics, which states that the total entropy change of the universe must be positive for a process to be spontaneous, which means delta S has to be positive. For a reversible process, delta H equals 0. For an irreversible spontaneous process, the delta S again has to be positive. To calculate the total entropy change of the universe, like we've done over and over, you're going to take delta S of the system plus delta S of the surroundings. If the entropy of the system decreases, then the entropy of the surroundings must increase by a larger amount. This is different than what we've talked about. When we've talked about enthalpy changes and heat exchange, we've always said it's changing by the same amount. But in this case, when one changes, the other one has to change by a different amount. It's not going to be congruent. When delta S of the system is negative, the delta S of the surroundings becomes positive and vice versa. An increase in the delta S of the surroundings also comes from the heat released from the exothermic reaction. When materials change state, the number of macro states it can have can change as well. So for entropy, we talked about this again. A solid is more ordered than a liquid, which is more ordered than a gas. And because of the degrees of motion of the particles, when you change from a solid to liquid to gas, you're going to change the entropy of the system. So if we look at this graphic showing you kind of a heating curve of a substance, you're going to see the entropy increases as you go from a solid to a liquid to a gas. When a system process is exothermic, it adds heat to the surroundings, increasing the entropy of the surroundings. If you think about it, if you're giving off heat, the temperature is going up, the particles are moving more quickly, the entropy is going to go up. The endothermic process is the exact opposite. In endothermic, the temperature of the surroundings is going down, meaning the particles are slowing down, which means the entropy is going to decrease. If the amount of entropy change of the surroundings depends on the temperature, meaning the original temperature, meaning what it started at. Of course, if it's starting at a very high temperature, where it goes really depends on where it started from. The higher the original temperature, the less effective addition or removal heat has. If you think about it, if they're already so crazy, if the particles are already moving around so fast, when you try to change it, it's not going to have a large effect unless you get a very large change in temperature. To calculate the delta S of the surroundings, you can use negative delta H of the system over T. Remember, T is going to be temperature. Gibbs free energy with a symbol of G is very similar to the free energy that we talked about before. Gibbs is a person who discovered this, which is why it's going to be a capital G. This is the maximum amount of energy from the system available to do work on the surroundings. Again, it's free energy, the amount of energy that's free to do work. To calculate delta G, you can see there's a number of ways you can do it. You can take H minus T times S. The delta G of the system is equal to the delta H of the system minus the T delta S of the system. And then you can also do what we do before with the standard free energy. Look up the free energy in the charts and take the sum of the product free energy minus the sum of the reactant free energy. When delta G is less than 0, there is a decrease in the free energy of the system that is released to the surroundings. This process will be spontaneous when delta G is negative. Delta G will be negative if delta H is negative and delta S is positive, or in an exothermic reaction. When delta H is negative and large and delta S is negative but small. When delta H is positive but small and delta S is positive and large. So if we look at this, delta G and delta H, for the most part, are going to be in a direct relationship. When delta G is negative, delta H is going to be negative, and vice versa. And usually delta G and delta H are opposites of delta S. So what's usually going to happen is if delta G is negative, delta H is negative, and delta S is positive. When the opposite is true, when delta G is positive and delta H is positive, delta S is going to be negative. The changes come in, or the differences come in when we're talking about a very large amount of one or the other, of delta H or delta S. So if delta H is negative and very much larger than delta S, it's kind of like the delta H takes over the system. So if we look at these numbers here, if delta H is negative, delta G should be negative. That's the rule. But if delta S is negative, this tells me delta G should be positive. But if we notice, delta H is larger than delta S. So it kind of takes over, almost like somebody who takes over the conversation. Delta H is going to take over the sign of delta G in that case. The opposite is true for the other case. So if we look, if delta H is positive, delta G should be positive. but delta S is positive, so delta G should be negative. But since delta S is bigger, taking over the conversation, then delta G is going to be negative in that case. When delta G is equal to 0, the reaction is at equilibrium. So this chart here just summarizes what we just talked about. When is delta G negative? When is delta G positive? Remember, the normal case is that H and G are always the same sign, and S is always this opposite sign. The differences come into play when we talk about whether we're at very high temperature or very low temperature. We can also get standard entropies. These are going to be things that are in charts. It's always for 1 mole at 298 Kelvin, basically when something's at STP. Gases, liquids, and solids, we talked about this a lot. The entropy order is always gases are less than liquid, which are less than solids. For molar mass, the larger the molar mass, the larger the enthalpy. Allotropes, remember, are different forms in the same state. The enthalpies are different because of the different arrangement, things like graphite versus diamonds and O2 versus O3. Molecular complexity, the larger the molecule, the more atoms it has, the more entropy it's going to have. And generally, dissolved solids have a larger entropy than the solid form. The third law of thermodynamics is that there's absolute entropy of a substance, and this is due to the dispersion of energy through its particles. So for a perfect crystal at absolute 0, the entropy is 0. That is when we get a total orderly system. Again, this is a standard. Generally, this doesn't happen. Just when we talked about, standard pressure and temperature and ideal gases, these are in a perfect world. These things generally don't happen this way. So every substance that is not a perfect crystal at absolute 0 has some energy from entropy. The absolute energy is always a positive endothermic reaction. To get the standard entropy, we're going to do what we've talked about a lot with the standards. Notice the little degree sign that tells you it's standard. To calculate that, you're going to take the standard products, sum of the standard products minus the sum of the standard reactants. Same with G. To get the standard G, you can take the sum of the standard G products minus the sum of the standard G reactants. And then if you assume the change in delta H reaction and delta S reaction are negligible, then you can calculate delta G from delta H minus T delta S. If a reaction can be expressed as a series of reactions, the sum of the delta G of individual reactions is equal to the total. So this is very much like Hess's law we did for delta H. The amounts of material is multiplied by a factor, then delta G must be multiplied by that factor. And if the process is switched, then you have to switch the sign of delta G. Note that delta G is related to work and energy, while delta H is related to heat energy. Remember, delta G is Gibbs free energy. It's talking about the amount of energy available to do work, whereas delta H is talking about the amount of heat available to be released. The change in free energy is a theoretical limit as to the amount of work that can be done. So what that means is, again, we've talked about this a lot. Delta G can be calculated for a substance, but that doesn't mean that's always going to be the amount of work done. That is like at the absolute best case scenario, which usually doesn't happen. If the reaction achieves this theoretical limit, however, it is going to be reversible. Delta G equals the standard delta G only when the reactants and products are in their standard state. This usually means it's at 25 degrees Celsius, the pressure is 1 atmosphere, and the concentration is 1 mole. Under non-standard conditions, you can use delta G equals delta G standard plus RT ln Q, where Q is the reaction quotient. This is kind of like the ideal gas law versus the stoic reactions that we did before, whether or not it's at STP. At equilibrium, delta G equals 0. So we can use other equations like delta G equals negative RT ln of K, or K equals E to negative delta G over RT. We're going to do practice problems with all these, so don't worry about it too much. K is a constant again. So for an exothermic reaction, increase in the temperature decreases the value of the equilibrium constant. And for an endothermic reaction, increase in the temperature increases the value of K. The Van Hoff equation is another thing that's been technically taken off the AP exam, but I still think it's important for you to know. It's written here. We will do a few practice problems with it, but don't worry about it too much. And that concludes our lecture for Chapter 17, which is free energy and thermodynamics.